All right, class. Another good one here. Here's somebody doing some push-ups, and so talking about again the forces, and again, hopefully you'll be kind of really impressed at some of these numbers, especially if you look at how big the number is in the tricep muscle here. I'm going to be curious to get to it. Anyways, let's just read it. They've got a nice picture, so that'll help with our understanding here. It says, what force should the woman in the figure exert on the floor with her hand to do a push-up, assuming that she moves up at a constant speed? Okay, so for A, I would say, again, the sum of the torques should be 0, and the sum of the forces should be 0. Because at a constant speed, then you have no accelerations. All right. So we can use what we call static equilibrium for the case of constant speed, often referred to as a dynamic equilibrium. And so that's a little subtlety that needs to be mixed in with this problem, okay? And so I wanted just to kind of say that up front. And in this case, as she kind of extends her arms, her head and upper body is going to go up. And so she's kind of pivoting right here at her toes. And so let's pick that to be our pivot point, and let's go to the second condition of equilibrium. And I'll say it again, the nice thing about a torque is when you calculate it, you can have a force without having a torque if your R is 0. And so something like this, where we're looking for this reaction force, so she pushes down on the ground and the ground pushes back up on her. So I'm interested in the force back up on her, but they're equal and opposite. So the question really asks, how much does she push? But what I'm going to calculate then is how much the ground pushes back, knowing from Newton's third law they're equal and opposite. So, because the girl here is my system, and I want to then know what external forces, because she's pushing on the floor. And I don't want to study the movement of the floor. I want to study the movement of the girl. And so as she pushes on the floor pushes back on her. Okay, that's the important piece here. Okay, now, keeping all of that in mind, I want this one. I know this one. This would be nice if it was not part of my equation, and that's where the torque can come into do. If I pick this as the pivot point, the R would be 0. And so when I talk about how much torque do I get from the pivot point, it's going to be 0. And so when I say add up all the torques, it would be torque from the pivot point. It would be torque due to her weight. And it would be the torque due to her force. Your author here calls it reaction force. But as I said, all of these have to add to 0, and this first one is already 0. Okay, well, I think I'm going to need quite a bit of paper for this one. I'll put 0 equals. And as we just said, the torque from the pivot position, even though there's a force here, the torque is 0. And so when I go to calculate the torque from her weight, it looks like here's the line of action coming down. This is the perpendicular distance. So using this formula here, the perpendicular distance is 0.90 meters. The force is the weight of her, so that's 50 times 9.8. And I'm going to throw in a negative. I'll get that conceptually. So here's her pivot. Gravity would tend to make her go down. That's a rotation in a clockwise direction. Traditionally, we call clockwise a negative, so I'll stick to that tradition. And so this is a negative torque. Okay, so force and distance and a negative. Now, I'll put a plus because the force that the ground is putting on the woman is up. And that will tend to lift her up, rotate her in a positive direction or a counterclockwise direction, which is traditionally positive. So I'll call that a positive torque. And the distance is 1.50 meters, and the amount of force is the unknown piece. So that's a perfect recipe here. It worked out perfect. That even though there were two forces I didn't know, by picking one of the ones I don't know as the pivot point, I can get the other one. All right, so after a little bit of algebra, I will get this reaction force. Wait. It just dawned on me. It says, what force should the woman exert on the floor with each hand? So this force that I'm about to solve for is the total of the two hands pushing upward. They don't really show two hands, but hopefully it's kind of implied here that she's got two hands pushing down here. Okay, so let me calculate this, but then let me also cut it in half to get the force from one arm. So I'm going to go 0.9 times 50 times 9.8. And so moving that to the other side, it's a positive. So that's 441 Newton meters. Then if I divide that by 1.5 meters, the meters cancel off, and we'll be left with units of a Newton, and that's 294. Now, if I cut that in half and say this is her force from one arm or one hand, I can then go divide by 2 and see what I get. And so that's 147 newtons. All right. So 147 newtons from each hand, then a total of 294 lifting her up, which is rotating her in a positive counterclockwise direction, with gravity pulling her in a negative clockwise direction. Okay. All right. So continuing on here with this problem, then it says the tricep muscle at the back of her upper arms is in an effective lever arm of 1.75 centimeters. And she exerts a force on the floor at a distance of 20 centimeters from her elbow joint. I think in this side picture, it's kind of hard to see. So I'm going to attempt to draw kind of looking from this side, so just to the right of her, and seeing the top of her head. And so maybe I'll make a little circle. This is the top of her head. So her shoulders would be something like this, with her body extended backwards and her legs kind of tapering off and having a little foot here. And again, you can see I'm a terrible artist. But there's her body. What I really want to focus on is then her arms. And so let me put her shoulder right here. And her shoulder, her arms would probably come down to an elbow joint right here. And then her hand down on the ground. Of course, it would happen on both sides. Okay. Didn't quite get them to match. But hopefully you get the picture here as we take kind of a head-on view here. Because I want to focus right here. Right here, what they're saying is this muscle, the tricep, in the back of the upper arm, is then connected to the outer part of the elbow here. And they're saying that distance is 1.75 centimeters. So it's as this tricep contracts that it would tend to then rotate at the elbow joint and pivot the hand, this way, which is extending the body up. I guess if there wasn't a floor there, when this tricep contracted and pulled in the tendons, it would make the hand kind of rotate this way. So your tricep is used when your hand moves away from your body, whereas the opposite is true for the biceps. And maybe I shouldn't draw the bicep, but the bicep, when it contracts, would pull your hand towards your body. So, shouldn't have drawn the bicep muscle. I just wanted to focus here on this tricep one. See, because this right here is the force from the floor. Your author calls it this reaction. So if we were to just draw the elbow joint, we might say that with the hand here, this force, this reaction force, being a distance away, and I believe it said 20 centimeters. She exerts a force on the floor at a horizontal distance of 20 centimeters from the elbow joint. And they said horizontally, a horizontal distance of 20 centimeters. So they're saying that when you go to calculate the torque, R perpendicular times F, we would be using a 20 here, and this would be tending to move this arm, and I guess that'd be a clockwise direction. Whereas the tricep muscle would be right about here, contracting in as the tendons are hooked to the outside of this elbow. And they're saying it has an effective distance right here of 1.75 centimeters. And so, again, as we said back here, when that tricep contracts, it's going to want to move the hand in a counterclockwise direction. So let's use that second condition of equilibrium, that is the sum of the torques equals 0, to analyze this. And I would say then, calculating this at the elbow joint, I would have a torque from, and I'll put a little T for the tricep, and I would have a torque that is coming from this floor, which I'll just call it the reaction, like they did, okay? So putting in my numbers here, coming back to this picture, I would have the force from the tricep muscle and the distance away. Let me put it in as meters, 0.0175 meters. And let me point out that that's rotating it in a counterclockwise direction, so that's a positive torque. Whereas the reaction flow from the floor is then rotating it in this direction. That's a clockwise direction. That's a negative torque. And its force is what we calculated back here in A. And of course, I'm looking at just one joint, one arm there. Okay, so 147 newtons. And a horizontal distance of 20 centimeters, which I'll change to meters. So after a little bit of calculation here, I should be able to get the amount of force coming from that tricep. So I'll take the 147 times 0.2 for the torque, and that's a negative. I'll move it over the other side. It's now positive. Then I divide it by 0.0175, and the amount of force is 1,000 680 newtons is the force from the muscle and all the tendons in there. And I'll just say again, notice the force at her hand is only 147. So if I were to divide this by 147, it's over 11 times more stress on the tendon than on the muscle than what is actually being applied by her hand to the floor. And again, that's this whole conversation about angles and distance and the whole endoskeleton construction is your force has got to be pretty big. And again, hopefully your tricep can handle that in the sense that you can do a couple of push-ups and you'll be healthy and stronger for it, but you won't tear a muscle or anything like that. Okay, let's go on then to C. I think C is kind of a throwback to earlier problems because it talks about now energy. And so it says, how much work does she do if her center of mass, so right here, is to raise 0.24 meters. So this is force times distance. The force from gravity then is mgh, or that's the gravitational potential energy. So she's lifting the weight of her body, 50 kilograms times 9.8, and it says we're going to lift it about 24 centimeters, so 0.24 meters. So if I put in all my units, I will get a Newton times a meter, which then is a joule. Okay. So here I have 50 times 9.8 times 0.24. And so every time she does a push-up, she gives herself 117.6 joules of gravitational potential energy. Now, she probably burns more energy than that because not all the energy that is used in the metabolism shows up as useful. In fact, I want to say, if I remember from that chapter, we talked about the human body. In different conditions resulted in different results, but somewhere around 20%. So one push-up may give you this much external gravitational potential energy, but the total you do is 5 times that. So in other words, 4 times that shows up as heat in the arms and in the muscles, and and then your body has to get rid of that heat. And so that's how much you would metabolize. Okay. But this is what we would call her useful energy, how much actually came out, not the total of how much calories or how much energy did she use in the metabolism of it. Okay. And then that's why I think D says, what is her useful power? And again, useful, they're talking about this, not the amount of heat that is going to now warm the muscles and therefore we'll start sweating to cool and get that heat out of there. But the useful power, if she does 25 push-ups in 1 minute. And so, again, power is this work per time or this energy per time. So I would say her energy is 117.6 joules, but in 1 minute she does 25 of those. So I'm going to take that number and multiply by 25, and time-wise I'm going to divide by 60 seconds. So I will get energy per second, or joules per second, and so that is a watt. So if we want our answer to come out in watts, we of course need our energy in joules and our time in seconds. And so that's why I'm going to put here a minute worth of time, 60 seconds. All right, so taking that number and, like I said, multiplying by 25, that's the total number of joules after doing 25. And so if you divide that by the 60, it's 49 watts. And so during that minute, the power, useful power, is 49. As I said, the total is probably about 5 times more than that because 80%, so 4 times that is heat, and then the 1 is useful. And so you would probably be burning calories, burning energy food at a rate of 245 joules each second. Okay. All right. well, that had some trickiness into it, and hopefully that helped. Particularly the A and B. The C and D, I get it. It's just kind of throwback. But the A and B is what this chapter is centered on. All right, take care.